Hello everyone and welcome back to this next lecture. So in this lecture we are going to execute our trip zone project. So in this case the trip zone project requires a slightly different circuit connection, and that's what I will show you when I bring the microcontroller into the video. So with this you'll see the microcontroller in the video. Here of course the connections have been reduced to some extent. So for example, I have only connected one gate signal from each EPWM module. So for example, there is output A from EPWM1, output A from EPWM2, output A from EPWM4, and output A from EPWM5. These are the four eating signals that I am actually looking at. The others are complementary. We've already seen them. No need to see them again. Now the difference is in the connection of the trip zone input. Now we have configured GPIO 97 as our trip zone input, and that is this yellow wire here. That is GPIO 97. Now the problem is the trip zone input is active low. What that means is if the signal at GPIO 97 is low, then in that case it will be seen as a trip zone event, and that will block all your gate signals. So this is a problem because why? We cannot simply leave it as it is. We must connect it to VCC if we want to disable the trip input. And that is what this connection is. This connection, this wire here is connected to the 3.3 volts on the kit. So I have taken 3.3 volts and brought it to this solderless breadboard, and I'm connecting my GPIO 97 to the same 3.3 volts. This way, by default, I am stating that my trip zone is disabled. That means because the trip zone input is pulled high, therefore there is no trip zone event. Alright, so with this we are now going to try to emulate a trip zone input, and for that I am going to take this GPIO, this connection out, that is GPIO 97, and I will connect it to the ground pin, and we will see what happens to our gate pulses. So with this, let us start our project. So I will go up to the Bitfield project and move into the debug mode. And the usual question, choose CPU 1, click OK. And we are now in the halted state. So as usual, select it, run it, and you will see that there are gate pulses. Now I am not zooming in all that much because I also want to show you how I am going to emulate the trip zone fault. So you can now see that there are gate signals on the blue pin and the yellow pin. So the blue pin is EPWM1, which is a high frequency 10 kHz signal, and the yellow waveform is the output on EPWM2, which is a 5 kHz waveform. So with this, let me show you how I'm going to emulate it. So I'm going to take out this yellow wire, which is GPIO 97. And the minute I take out this wire, you'll see something very interesting happening on the waveforms. The reason is now the signal is undetermined. All right, it could be low, it could be high, and it is now seeing it as a potential fault. Now I'm going to connect it to the ground of my solderless breadboard, and you will see that now the gate signals are blocked because now this is seen. This is now, so the oscilloscope is running, but you will see there are no gate waveforms because this is now seen as a trip zone event. For example, if I were actually connecting GPIO 97 to the fault output of my power module, and the power module was giving an overcurrent fault, then in that case, this would block all the gate waveforms. So to revert, I'm just going to take it out, and you'll see again that fluctuating waveform, and if I connect it to VCC, you will see that the waveforms are back and they are steady. So now let us repeat this for CPU 2. So I will just go back here, connect CPU 2, and I will now go and load the program. And the program is loaded, and I will run it. So of course, to see it, I must change the connections. That's what I'm going to do here. I will just move this over Alright. So of course here you will see the waveforms behaving in a slightly strange manner. Let me just go. So you will see, and the reason for that is because their factors are different. One of them is a 15 kilohertz signal, or rather one is a 15 kilohertz signal and the other is a 4 kilohertz signal. So they are not actual even multiples of each other. That's why one of them is actually appearing to be running. Alright. So now that this is done, I'm going to now start the same emulation of the trip event. So what that means is I'm going to take out this yellow wire, and the minute I take out this yellow wire, you see the same effect. That is, the gate pulses are fluctuating. Now I'm going to connect it to my ground, and now with ground connected, you see that the gate waveforms are blocked. So once again, our trip zone event, our trip zone input has been configured correctly, which means if I give a trip zone event, or if I give a low signal on any GPIO which is configured as a trip zone input, that effectively blocks all the gate waveforms. So you see, the oscilloscope is in run mode and still there are no gate waveforms. And if I revert this, that is if I just take it out, you'll see the same effect again. The waveforms are fluctuating, and if I connect it to VCC, you will see now the waveforms are steady. So once the trip zone event has been removed, then in that case the gate waveforms are restored. So with this, we now have concluded on the trip zone submodule. So with this, I will end this video, and I am also at the end of this lecture. And with this lecture, I am also at the end of this particular section. So if any of this was not clear to you, or you have any other doubts, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will conclude on this section in the next lecture. Thank you so much for listening, and see you soon. Goodbye for now.